what are we trying to prove? Well, we're trying to prove that it's NP-hard to approximate max 3 set within 7/8 plus epsilon. And for a reason that's still obscure and maybe not so well motivated, I said I would do max 3 lin instead and then get a constant half plus epsilon. And something I sort of felt guilty about is I used the terms completeness and soundness over and over again. I never defined them. Completeness is the probability to accept a correct proof of a correct statement. Soundness is the maximum probability to accept something that's incorrect, an incorrect statement. And then I had some background. I said PCPs. I never told you what PCPs were. They're probabilistically checkable proofs. And the PCP theorem says that there's a polynomial size proof that with order log and random coins, you have a proof that reads a constant number of bits, which has completeness 1 and a soundness that's an absolute constant less than 1. And then I did the two-prover game, turned this into a two-prover game. Well, first I actually assumed that this was, let's do this. First I sort of cheatingly assumed that this was 3, and then I turned this to a two-prover game. Of course, the PCP theorem is a difficult theorem, and I didn't prove it. I just stated it. And then in this two-prover game, I just said you could play this in parallel. And then you kept the perfect completeness, and you improved the soundness as much as you wanted, depending on the number of repetitions. And then I abstracted away this two-prover game to a label cover game, where you have a small side and a big side corresponding to the two provers. And the task, and you have edges going across, and each edge is a projection. And the task is to make labels for these things that respect the projection. And the completeness of this proof system is 1, that in the good case you can find labels that satisfy all the constraints. And the soundness is epsilon, where epsilon is this number. And then I said, well, what we actually should do in this label cover is we should replace each label by a big table, which was supposed to be the long code. And the long code, a correct long code, is simply something that takes the corresponding input and outputs the corresponding coordinate corresponding to the label. And on top of it, I wanted the long codes, these tables, to have the properties that they respect negation. And then I said I would choose 3 inputs, x, y, and z, the first 2 randomly, and then the last one essentially to be the product of the first 2 with probability 1 minus delta, and with probability delta I set it to something else. And before we continue, I just wanted to be brutally concrete. I mean, somehow nothing is very hard here, but I wanted really to see, what is this proof like? Okay. Now I should also. So let's just see what this proof system would look like. Suppose I fix the label here and a label there. Sorry, a position there and a position there. And the small set actually has 2 different labels, and the big set has 4 different labels. And the projection on this very edge happens to be that it maps 0 and 1 to 0, and 2 and 3 to 1. Okay. And somehow I specified the supposed long codes. And F should really be something that maps 2 bits to a single bit, right? Because S is 2. But since it's forced to respect negation, I just need to make the table for the entries that have a 1 in the first position, and then I will know what we're going to, when there's a -1 in the position, we'll take that thing and negate it. You're happy with this? And G is a function of 3 bits, and I just need to specify it for all the inputs that start with a 1. So let's start. So what's FU here coding? The second bit. Excellent. You disqualified yourself on top. So what does G code? Yeah, did I get this right? Yeah, it codes the third bit. Yeah. Right? So now to do my protocol, I picked 2 random inputs. Okay, and you don't trust my randomness anyhow. But I picked X to be this random input and Y to be this random input. And then now let's see how we should compute Z. So let's assume delta is a small number here. So let's assume that there are no errors. That's actually. So then what should Z be? Pardon? 1, 1, minus 1, 1. So how do we calculate this? Well, I should start. I shouldn't make. Yeah, so what's this one? Well, we should take this corresponding coordinate in y, and we should take the corresponding coordinate in the projection of x, right? So if you see that pi projects 0 to 0, so this one is the XOR, which is just a multiplication of these 2 bits. Similarly, this thing is the multiplication of this bit and that bit, since pi also maps 1 to 0, right? And then this is the XOR of this and this bit, since it maps 2 to 1 and it maps 3 to 1. So that's actually okay. So let's try to compute f on this. Okay. Well, minus 1 and 1 is not in the table, but it's actually the minus of this. So f of x is actually 1. Right? It's minus f of 1 minus 1, which is 1. G of y. Well, we have minus 1, minus 1, minus 1, 1. And then we need to negate everything, so but we have 1, 1, 1, minus 1. So it's minus g of 1, 1, 1, minus 1, which is 1, and g of z.
Minus g.
Good. There were too many of you to get chocolates for that one. And g of c, well, yes, we have to look. 1, 1, 1, minus 1, 1. And it's a minus 1. And you see the product of these 3 bits are 1, and then we should accept. Okay? Yeah, I also claimed some properties of this protocol, which I'll recap soon, but this is sort of the setup of the protocol. So are you all happy? So in the end, this was sort of important to set up, but if you just remember the label cover, well, it's not completely true. We might have to go back a little bit later, but for now, we'll just use the label cover. Is everybody happy with things? I also had a name for this, but I think I forgot to write down. I think I called it.
Johan, you misspelled completeness
Did.
then. Did I get a chocolate for that?
Nah, trivial misspellings is trivial mathematical errors will cause chocolates, but you know, obvious misspellings will not. Okay. No, so the soundness, the completeness lemma I did last time, saying that if a correct labeling of a labeling that satisfies everything, and you just follow this recipe, you use the long codes here, and then you check this equation, and that satisfies exactly when you choose this alternative on the important input, you know, the correct labeling. So were you happy with this, or do you want to see this again? Anyone? I'll show this again, okay? So what's happening in there? Well, we pick U and W. So the point is that right? So by the definition of the long code, this should be the very coordinate for which you're coding, because G and for the same reason, GWY is Y with the same thing, and FU of X is X to the label corresponding. Sorry. That's what happens in a correct proof of a correct statement. But the important property now is that pi of lambda W is lambda U, which means that with probability 1 minus delta, we had Z right, because that's how we define the probability distribution on the XYZs. Okay. So we really set up everything to just have a very easy completeness. You know, a correct proof of a correct statement is sort of, it's, one should see what it does. Okay. So the important soundness lemma is now that says if you have a good proof in this, with this acceptance criteria, and good here would be that you accept with probability at least half plus gamma. I call this delta prime, but then sort of this formula became difficult to read last time. So if you accept with a probability that's a little bit more than a half, then in fact you're going to extract a labeling that does something interesting for the label cover thing. And it will in fact satisfy a fraction of the label that depends only on this number and the defining number here in the, okay. And the point, the logic now is that if you set up things so that this is actually bigger than epsilon, which we know was the soundness of the label cover, then we know that such a thing cannot exist. Okay? So the next thing I wanted to do is actually start proving this soundness lemma, I think. Or do I need to review how that gave the inapproximability for max 2-lin, max 3-lin? That was sort of this, the bad prover, right? That sort of sets himself to optimize the best proof, and then it's really the completeness over the sum that gives the approximation ratio there. You know, this unscrupulous prover that just tried to convince the verifiers as quickly as possible. Well, if you have to return to this, we'll return to this later, but we'll... Okay. Yeah. How do you spell this like this? No. Well, never mind. So we'll fix, let's fix the edge picked, which sort of means that, and from now on I'll use f, g, and pi without indices, you know. F depends on u, g depends on w, and the projection depends on both, but let's ignore this. Okay. So let's write down some arbitrary quantity here. I mean, the product of f of x, g of y, and g of z. What do we know about this?
Well, the acceptance probability of the verifier is a half plus a half of that.
Yeah. So this is... So you're saying that this is 2 gamma, right?
Yeah.
If I usually, well, let's do like, let's make my life a little bit harder. And I don't have to drag this too along. The expectation of this is just gamma, right? Sorry. So let's see what it looks like. So now I'll just replace this by the Fourier expansion. So we'll just have, well, we've seen the Fourier expansion in the 2 other talks, and I hope I can do this without explanation. So we'll replace this and this and this. So this expectation just looks like the expectation of... Let's do it carefully. What? I realized this already because, yeah, changing this delta prime to gamma was a bad thing, but that's, we have to live with this. Yeah, you have to improvise sometimes. Yeah.
Dan, I think you want to change it then.
Okay. Didn't do a lot.
Look at what big one is.
Yeah, so you just expand the sums, so you get the hideous three big sums, and then you know expectations go inside the sums, and then we just have to look at this thing, okay? And now you have to remember, is everybody happy with this? You know, you expand it, you know, you change the order of expectations and sums, okay? So let's see. Thanks. So this is what it actually says, right? In the plus minus one notation, the characters are just the products. Okay. So let's take the expectation of this. So what the main thing we want to do is we want to say that this is 0 most of the time. Anybody who hasn't seen this who can actually figure out some terms that are 0? Yes?
I'm not answering, I'm just asking that. So does not it bother us that alpha is somehow in a smaller domain, is a Fourier coefficient, I mean not Fourier coefficient, is like so the x, I mean the chi alpha is a Fourier.
Yeah, so these live on slightly bit different.
Sorry?
These live on different domains, so I should really have, you know, S and L here, right?
Yes.
That's what you're saying.
Yes, so does not it bother us? So that's my question.
Well, even though I suppressed it there, the expansion is correct, right?
Yeah, the expansion is correct.
Yeah.
No, I'm just saying that so far we have learned.
This is something we have to take into account. Yes, surely. Huh? Yeah. So let's see. Okay. So my first claim is that if you look at the term like this, and these two sets are not the same, I claim that the expectation is in fact 0. Okay. And the reason is, you know, suppose we fix x. Well, each yi is a random independent bit. Zi is very dependent on yi, but independent on everything else. So unless both zi and yi appear simultaneously, we'll be fine. Okay? I get some curious. This is just the orthogonality of these Fourier parities, essentially.
Projection of beta.
Pardon?
As well, if the projection of beta doesn't include alpha.
Yeah, so I'm fixing. Let's fix x.
Yeah.
So then we just have to. Then this is just a constant, right? And now I'm just worrying the random choices over y's and z's. And I claim if you look at yi and zi, they're both independent.
Yeah,
they're random
I'm
bits.
saying that it will be 0 as well if beta won't include alpha.
Oh, good, good, good. Yes, yes. You're moving ahead. You know. Okay.
Hey, Johan, yi and di are dependent, right? But yi and di prime are independent, right?
Yes, yes.
So the second zi should be zi prime or something.
No, 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 no. I wasn't finished with the sentence. Yeah, so what I wanted to they're independent of everything except each other, right? So if Ci appears in this and Yi does not appear, we're fine. Was this a mathematically clear statement? Okay, thanks. Okay. So we
This is in the case that that you don't add noise.
yeah, I don't need the noise for this.
No, I'm saying that if Zi is with probability delta is not, it's minus. Okay.
I mean this.
Okay,
I mean,
yeah,
if it
it's
delta
always-
is zero, it would be fine.
Yes, you're right.
Okay.
After you fix the noise.
Yeah, you can view it in various ways, but you know, there's still noise or no noise. They're still independent of. Okay. So this means that we sort of and I had already forgotten the beta prime there, so it's fine. Right? So this says we can discard all the terms where beta is not equal to beta prime, and we get something like this. Okay. So now with the question, we had some who was trying to get the chocolate here by getting rid of some more terms. Would you want to continue?
I just said that if beta doesn't contain alpha, then it will be equal to 0 as well. Then alpha is inside beta.
Well,
and actually is otherwise
but beta and alpha live on different spaces, right?
Z projection.
Yeah, okay. So you're claiming that okay. It is okay. So could you argue this? Does everybody agree to this?
Sure. Isn't the inclusion opposite?
You want to do it the other way around?
No, don't we want alpha included in 5 beta?
Now we have a different bet here, unless alpha. Right, this is what you're claiming. Oh, sorry, yes. Now we have, maybe they have to be equal.
That's conjunction of these two things.
Yeah.
No, equal doesn't suffice because if you have two y's that collide, they will cancel each other.
Yeah.
So you have to look at the numbers that appear in y in pi of beta odd number of times.
Okay. Did everybody get this? No. So so which of the two statements would you claim is correct then? Which implies that the term is 0?
Pi of beta plus alpha should be 0.
Isn't it better to replace the yi zi by 1 minus 2 delta and put the x out so it's more transparent?
Huh?
The expectation of y zi is just 1 minus 2 delta.
But it's not
And then you
independent
get
of
x,
x.
and then you get the x pi I.
Well, so let's try to make this a little bit more transparent then. Okay. So let's write this as mu I times x pi I times yi where the probability that mu I is 1 minus delta, and the probability that minus 1 is delta. Okay, is that what you, that's the best I can do. So I'll sort of explicitly do this error, and then everything is sort of independent. Okay. Right? Did I get this right? So now we sort of, this is a biased variable, and we sort of have the yi's, and we can cross out the yi's, since there are 2 plus minus 1s that in fact square to 1. Okay? So now you see, well, Hanan, I'm sorry, that was an excellent suggestion.
I read your paper.
Sorry, whoops. I'm sorry about that one. Please redirect. Yeah. So now we can look at this. Is this always 0? So the point is now we have to have a product of xi's, which are sort of uniformly random things. So either we have an empty product or we get 0. So my claim is now that the only way we can get an expectation that's non-zero is that if all the j's that appear in alpha, something appears in alpha if and only if there's an odd number of i's that project onto this thing. Which sort of means that we do have this condition, but we do not really have this condition because an odd number of betas that project, sorry, an even number of betas that project onto the same thing will actually cancel each other. Okay.
Johan,
Yes?
could you please repeat how you got this yi times x by I times yi?
This one,
No, the noise, that's the noise, right?
yeah, this is the noise thing that I tried to introduce here.
Yeah, but the previous 3 terms, how did you get those 3 terms? I mean, you had 2 terms to start with.
Are you referring to this equation?
Yeah, yeah,
I expanded, I had the beta and beta prime, right?
yes.
And then I claimed that unless beta was equal to beta prime, it was
Yes.
0. So then I kept only the beta terms. And then I had yi times zi. And then I just replaced zi by its definition.
So you place
Zi was now the error vector times the x vector times the y vector.
Okay, thank you.
And then I canceled the y vectors. And then I checked that, to cancel the x vectors, we needed this. So this I'll use the shorthand saying that alpha is the mod 2 projection of beta. So I'll have this. This is exactly this condition. So beta uniquely defines alpha by this property. So everything has cancelled now except these error vectors mu I. And I only keep the terms where alpha is, this is summing over all, and let's just even do it like this. Pi 2 of beta, and just having the sum for beta.
So just a question, is
Yes?
this equivalent to actually having set it up as a homomorphism from GF2 to the first line to GF2 to the second line? You're talking about as a mapping of sets, but
This pi 2 condition, I don't know what is equivalent. I mean, I'm having an element that lives on this smaller space, right? And I'm lifting it to a vector on the big space. Right? X is really living on the small space, but then I say, let's look at it something on the big space by taking everything that projects onto to J to be Xj. And that's what it is. I don't know. I don't know if it's, I don't know how to say this better. Maybe there's some abstract say.
No, sir. Can you write it in terms of linear algebra over GF2? If you want, this helps.
Yeah.
but then they cancel.
Well, we can. So now we just need this expected value. Okay. But also this expected value is very easy because the mu i's are just random bits. That's 1 with a certain probability and minus 1 with a different probability. So I claim that what we get or maybe somebody should earn in chocolate. What's the expected value here? What?
1 minus 2 to the size of beta.
1 minus 2, not 2, the size of beta. Sorry. So this is what we have, right? So we have that gamma is in fact equal to this. Gamma, the acceptance probability over a half. We just dropped all the terms that were 0 and we calculated an expected value perfectly. Yes?
The expectation there is not 1 minus delta to the size of beta minus delta to the size of beta?
Pardon?
The expectation, why it's 1 minus delta, 2 delta to, it's not 1 minus delta to the power of beta minus delta to the power of beta?
No, I mean it's done independently for each I, right? We're not treating the things with the
yes,
projection.
Okay.
Okay.
Okay. It's
Yeah.
not 0, it's minus 1 and 1.
Yeah. Oh, okay. Good. Okay. So, but I cheated you. We do have, still expectation of u and v outside this, really.
The 1 minus delta came from this odd thing.
Pardon?
That this odd number of i's don't project to J.
Well, could you repeat the question?
So that condition
Yes.
that everything you get is an even number of projections.
Well, I mean, the only terms that remain is when this set really is the mod 2 projection of this thing.
Sorry?
I repeat the question. I'm not sure what
So that condition, how
Yeah.
does it appear in the formula? Does it appear in the terms of 1
Yeah,
minus
yeah,
2
and the
delta?
subindex of the FI.
this says, that we're just summing over.
Alpha is gone, you just sum over beta.
Right? Yeah, I had the sum over alpha, then betas and beta primes, and now I just reduce it to sum of beta.
But alpha is uniquely defined by beta,
Yeah.
by this condition.
So first I noted that beta prime had to be equal to beta for the sum to be non-zero, so I could drop the summation over beta prime. And then I noted that alpha has to be equal to the mod 2 projection of beta unless the sum is 0, so I can drop the sum over alpha and just.
Also that pi 2 beta means this
Yeah,
condition.
that's the-
This is exactly this condition, yes.
That condition, sorry, I didn't.
Yeah. No, that's
Thank
this
Give
stuff.
it this name.
Yeah, sure.
Okay. So the question is now what's the best thing to do, but I'll try a different way compared to I do it usually. So So what will I do now? You know, I'm supposed to take these Fourier coefficients, and I'm actually going to jump to the end of the proof and define the good labeling. You know, how do you extract the good labeling from the? How are you going to eventually extract the good labeling? So I claim that the labeling we'll construct is actually just going to, what does it do? Well, it's supposed to get an element to the left, which corresponds to a function. So what we'll do is we'll simply take the corresponding Fourier coefficients, and we'll return a random element in this Fourier coefficients. This is what we'll do on both sides. So now we can worry about lots of things. So anybody's worried about anything? You know, you have to check that these are reasonable strategies. At first I just said, you know, is this a good probability to start with? Yes?
If alpha was the empty set,
yeah, that's another problem. If alpha is the empty set, that's also lots of things to worry about here. Okay, that's a good worry. Thank you. Sorry, I should practice this more, you know. Or you should sit in front if you're going to say something. Let's keep this. Okay.
You haven't exploited the folding yet.
Right. So we sort of have at gamma is the pi 2 beta, g hat beta squared, 1 minus. Okay. What?
Alpha and beta too big.
Yeah, so if they're, yeah, you can worry about both their, so first of all, this was the first worry, right? So anybody sees the
So f is an odd function, right?
Yeah.
So all even Fourier coefficients are 0.
Yeah, you lost the chocolate there, right? But that's life, yeah. Yeah. So right, we have that f of minus x is minus f of x, which means that f at empty set, which is just the expectation of f, is in fact 0. I mean, we really have that f hat of alpha is equal to 0 as long as the size of alpha is even, but this doesn't matter for us. I mean, we really care only about the empty set. So this sort of says that okay. This really says that they are non-empty. They contain at least one element. Okay. So the next thing is that this I'm maybe not even going to have that chocolate. These are actually probabilities, right? There is sum to 1. So, well, success is, well, the key thing to analyze. So, let me, sorry. So I claim that the success probability, at least if you sum the Fourier coefficients, take only the sets that actually do intersect. And, let's do it like this. Suppose that alpha is actually a subset of the projection of beta. Then I claim, well, the probability of picking the set alpha is this, the probability of picking beta is at least this. And once you've sort of fixed the choice of a random j in beta, the probability that you'll there is at least one I that projects onto it, and the probability of picking this is at least this. Okay. Of beta is, fixed choice of j in alpha, and then the probability, we have at least one good I in beta, since we know that something projects on it. So, and the probability of picking this is at least 1 over the size of beta.
This pi to disappear.
Well, yeah. So if I say, well, instead of picking that A is a subset, let's say that I restrict this sum to when alpha is exactly pi 2 of beta. This is going to be more. Because, the pi 2 projection is always a subset of the projection, right? So I claim that if I change the condition to this, the success is still good. So now I only have to compare this, right? So now I have one expression that I know is large. Well, I have one success probability that sort of looks a little bit the same, and I now just want to compare these two guys. So now you just have to be a little bit smarter than I was when I wrote the paper in the first place. So you want to use Cauchy-Schwarz here. So if you use Cauchy-Schwarz put it on the sum, we sort of had, well, these are numbers smaller than 1, so it's sort of, we have the square here, and we sort of just have the first term here. So let's use Cauchy-Schwarz, and we'll see that we get the square here, and then we split this into 2 factors, and push 1 to the other side of the Cauchy-Schwarz. I don't know if Cauchy-Schwarz is magic to it. Maybe there are other ways to do this, but then this second thing is smaller than 1, right? Because it's again Plancherel. So this is smaller than just taking this thing out, going down. So so let's see what we have.
should be gamma square.
Is it 2 beta in 2 corresponding?
Yeah, it should be 2 beta. Thanks. So this sort of says that, you know, we look at gamma is smaller than this, and since expectations of squares works nicely, you know, the expectation of the square is better, it's more than the square of the expectation. We see that gamma squared is smaller than this, so this is large. So we just need to compare these two things. And, well, the simplest let's try it like this. And now you just have to observe that, in fact, this, for small betas, this is a little bit larger, but it's never larger by more than a factor of delta, and then we're done. Right? We define this strategy with the success probability, and since this term-wise is in fact greater than a factor of delta times this, and this is at least gamma squared, we are now done. And that's sort of the end of the soundness part. Any questions or thoughts? Or so this means that this is greater than delta times gamma squared, because this is greater than delta times that. And that's the strategy for that's the probabilistic labeling that we get, and then we're done.
So somehow all the betas that are less than 1 over delta, they're not important? I mean, because it's a terrible bound in that regime. So.
Yeah. Yeah, why does it work? That sort of, why doesn't, yeah, this is a bad bound. It's sort of, yeah, it's a sort of an accurate bound when the size of beta is about 1 over delta. But yeah, I don't expect this would be essentially tight. I mean, it's tight in that regime, so it means we can't do better in general. I mean, maybe you could do something better in general.
All you care about is some strategy that manages to satisfy a tiny constant fraction of the label cover. So it's a very bad bound, which means that you'll satisfy an even smaller constant, but you don't care about it.
Yeah, it's not a very bad bound. I think it's a...
It's wonderful.
But the point is, I mean, you can sort of see, I mean, when you set up this strategy, you can set up this strategy by the Fourier coefficients, and you say, well, you immediately come, what if these Fourier coefficients are large? Okay. Because then you'll have big, huge sets to choose from. But the point is, you need some damping factor here that sort of says that the big betas won't contribute to the accept probability in the PCP. And exactly how quickly this decays will sort of relate to the sets of the betas, I mean, the sizes of the sets, and you know, and the probabilities. So the faster it decays, the better, but this decays pretty nicely.
Is that the intuition behind the test too? Like, why would you think of this test?
I don't know. You can't have perfect completeness, so then I did. You know, I don't remember what I was thinking when I decided this the first time. It's a long time ago now. Yeah, in retrospect, you can have all these good arguments, but somehow when you prove things, you just fiddle around with it, and then something suddenly works, and then you sort of go back and analyze it. But it was clear you couldn't have perfect completeness, right? When you go for max 3 lens, you have to create some errors. And this seemed like a natural way to create errors. Okay, yes?
So when you say want to prove, so why do I want to prove? Do I want to prove because I want to, so is not there a story behind it that like I want to create a probability distribution which is according to G beta square on the labels or something like that, and that's how I am creating this label cover, or
I don't know what you mean.
Is this the reason I want to prove, or so?
Well, I want to prove hardness for max 3 sat was what you really want to do, right?
Yes.
And then and then I.
Yeah, but why exactly? I mean, there is a formula, and you are saying that I want to prove this. So I am asking, why do you want to prove that?
Oh, this one.
Yeah.
I mean, this was the success probability of the strategy I defined, right? This was the accept probability in the PCP. I mean, it was sort of derived from the success probability in the PCP. So the conclusion of this was that if the success probability in the PCP is high, then this strategy is successful. Sorry, maybe I didn't spell out this point, right? This is the success probability of this strategy I wrote down. Pick a random alpha with this probability, a random beta with this probability, and then just random elements.
That's the label.
Yeah,
so
that's the labeling, probabilistic labeling strategy. So the way to prove that this works with high probability is to compare it with the success probability of the PCP, which we assume is big, right? And these are, in fact, that's bigger than that term-wise, apart from the factor delta. I mean, these are all I mean, everything is positive here, so we can do it term by term.
Sorry, I didn't get
No, I'm sorry.
I'll
thanks for.
Did not get this either.
Good. Okay, so that sort of ends the 3-lin proof. So now we can try to do 3 sat. Okay. So this sort of does this. Okay. So in fact, if you think about it for a while, you know, a 3-lin condition is just, in fact, equivalent to a 4 clauses in 3 sat. And I hope I got it right. I need the other way around. Yeah, thanks. So in fact, something that satisfies this will satisfy all the 4 clauses. So right, so I can take what's the most simple of all gadget reductions. So I just replace one condition of these by 4 conditions, and it has the property that if this is satisfied, then I satisfy 4 clauses. And if it's not satisfied, I only satisfies 3 out of the 4 clauses. in fact, if you just look at it, if you just do this translation, if you can satisfy a fraction 1 minus epsilon of the clauses in the max 3 lin, you get 4 minus epsilon of the things over there. And if you do half plus epsilon, you get 3.5 plus epsilon. All right? And then you see, by picking epsilon suitably, this is as close as you want to 7/8. So we're actually done, yes?
I have 2 questions. One, first, it might be the case that max 3 sat, given that the formula is satisfiable, then you can do better. Because,
yeah. That's an excellent question. It's well worth of a chocolate. Yes? And?
The second question is, all of this reduction is randomized reduction. Can you make it deterministic? There are a lot of randomization in there.
No, the reasoning is randomized, but the reduction itself is in fact deterministic.
You need somehow to go to the parallel repetition, to the labeling, to the...
No, it's all, I mean, we're talking in probabilistic terms, but in fact, if you looked at the entire game, looking at all the random, right?
All the options random.
I'm always looking at all the random choices of the verifier, right? And I'm sort of making copies for all the, so there's no, so it is a deterministic reduction, okay? So the other question is excellent, right?
What was the first question?
The first question is, well, this is sort of, it gives the right approximation factor, but it doesn't give us what we want, right? Right? I never, mind you, I only promised you an approximation result. But maybe what you were thinking all along is that this is sort of aesthetically not very pleasing, right? You would really want, in the positive case, to satisfy all the clauses. But the ratio is fine. I mean, I can get arbitrarily close to 7/8 here. So, but it's a good point. And this is what we're going to do next, right? I mean, this is what we're going to work a lot harder for. But before we're going to work a lot harder, let us... I said, we can do a gadget reduction, but what's sort of the obvious way you're going to make a PCP? I mean, what's the obvious way of proving an approximability result? Well, why did we get max 3 lin here? It's because we checked the linear equations and the bits of the proof. So we really want to check this first to check a 3-sat condition instead. So let's do this. So let's make the final check here instead a 3-sat condition, instead of checking a linear equation. So first of all, what happens to completeness?
So are you still folding the code?
I'm still folding the code, right?
So you never have to check the negations or something like that?
Yeah, so that's like I never had to check equations equal to -1. I mean equal to...
You never have to negate the variable.
Yeah, I don't need... I mean, this will be some implicit negations in these things depending on the folding, right? So when you translate it to a... Well, you just have to check that these 3 bits are unlikely to be 1, 1, 1. And in the current proof, they actually are. But suppose we do like this instead, just to be on the safe side. Okay. Then I claim, completeness will work exactly as before. We'll just see, well, if these are correct codings of correct things, then these 3 bits will be the corresponding 3 coordinates of the y's, and they will with extremely low probability all be false. Okay, with probability delta. Okay. So you're happy with this change to the verify? I have the same probability. I changed the sign here just to be vicious, but essentially the same probability distribution of x, y's, and z's. And now I just check a very different condition, and then I hope to get the results for max 3 sat instead.
But then you don't have to introduce error, no? So that's the whole point, that now you don't want to introduce error.
Good. Okay. So now there are two things. So now you sort of want to set up the machine and say, well, I proved the soundness where we check this other condition. Now I want to prove the soundness where we actually check this work condition. You know, will this work equally nicely? And then you want to modify the distribution here so that you always accept, right? So any ideas for this? Well, any comments on either of these two things?
You can put a hard encoding.
Pardon?
You can just force for Z to be.
Yes, you have. Of course, it's an extremely difficult question because we want to analyze it. So you want to. Sorry, I stopped you in the middle. You wanted to say something.
Yeah, that's what I want to say. That you can force it and then try and see what happens to the analysis.
Right, so remember that false is 1. So the really thing, I mean, when you're going to choose some new distribution, the x, y, z's, what you really want is that these 3 bits should never simultaneously take the values 1, 1, 1, because then you lose. That's how you.
You can choose the delta only when y is minus 1.
Yeah. So now we have. Okay. Yeah.
So this is kind of what Dilur did now. So this is, I think that she did it just in a single long code as opposed to like 2 long codes.
I don't know what this. This happened before Rit was born, more or less. No, I think it happened before she entered academia. So, how old is she?
No, she was already a master student.
Oh, she was yeah.
But yeah, what she did was taking this ID and using it, basically.
But that's what she checked, no? We accept.
Yeah. She used this ID to test the long code.
Okay. Well, I'm not sure what paper you're referring to. What?
Your famous.
Yeah, I did it first. That's all I can say. But maybe. So let's see what conditions should we have on these 3 bits, right? So we had one suggestion here, you know. So you said we pick x randomly. That's what you said. And then we pick y randomly. And then you said, you know, we put zi equal to if these are both false. Well, so let's do what you. Let's try the thing we had. Okay. So this is more or less what you said, right? So any stylistic opinions on this? Okay. So first of all, something I never really said. What's the difference between y and z here? In the original. Or is there? Are they the same or they're different?
The marginals are the same, which is uniform random, but they're correlated.
They're correlated, but is x or y are they y and z? Are they I mean, if you changed if you picked z random. Yeah. So my point is that they're really symmetric, right? So are they symmetric here? Okay, so they're not symmetric, which is sort of a stylistic. On the other hand, x and y are random. Is the question is z random?
No, that's not true. I mean, you mean unbiased?
Yeah. Oh, sorry. Yeah. Is it uniformly distributed? Is what I meant. Is it or is it not? It's the danger is that z is not uniform. And the problem is that bits that produce zi and zi prime with the same projection are correlated. Okay. And the reason is that if x for this projected value happens to be 1, then they're both more they're more likely to be 1, because you know if the yi is okay. So when every one of your input is not sort of not uniform, you could get into lots of trouble. You really want them to be uniform.
So if x is 1, then you set yz to be 1 minus 1 or minus 1 1 with equal probability. Otherwise, you choose the same task.
Yes. So let's see if we got this right. So we. So the thing I actually want to do is that if the corresponding x is false, then I'll set yi and zi to be its opposite with probability 1. Okay. While if we already x pi is minus 1, then we don't have to care so much, and then for symmetry reason I'll set them equal with high probability and unequal with small probability. So this is in fact apart from how you vary delta, this is the only way how to get a distribution such that avoids 1, 1, 1, and such that y and z are uniformly distributed. So we don't get any pairwise.
So why don't you want zi not equal yi with probability 1 minus delta? Why isn't the minus sign up? Yeah.
Why you want it?
No. Why aren't they flipped there? With probability 1 minus delta, why don't you want zi equal to minus yi?
Well, so let's see if we'll see that from the analysis eventually, okay? But what happens is, well, if you look at just y and z now, this sort of says that in this case they're most often not equal, okay? So somehow, but you want them to be as random as possible, so when you have the possibility you set them equal as often as possible. But that's, yeah. So this is in fact the probability distribution.
The other way to see it could be that we are trying to be close to the parity question that we were asking earlier.
That's an excellent, yeah, we're actually very close to the parity distribution. That's another, right? This is saying sort of that the product of x, y, z almost always is minus 1. Okay, and it's not obvious why this is true, but this is, we're close to the parity distribution. That's a good point. Which is not clear a priori why this is beneficial, but that's, we succeeded there, and if we change little, we do well again. Okay.
So we are like close to the opposite of the parity, right? In the parity distribution, we wanted the product of the three.
Yeah, but I cheated. I already did this.
Oh,
here.
like parity distribution is already this.
Yeah, I already changed this to a minus.
Yeah.
To make sure that we're almost always satisfied. So that then, and it's very close to that distribution, right? So let's. So let's try to start the analysis, and we won't really finish it. So let's have this test, and we can have two different distributions. Both this sort of the negation of the parity distribution and this distribution that actually gives us the perfect completeness. Or you have, this will give us the perfect completeness. Here we'll have a PCP where the verifier always accepts, right? If you do, should I write this down? Because in a correct proof of a correct statement, you'll read 3 such bits, and if the first doesn't do it for you, one of the other, second to the other 2 will definitely do. Was it? Let's write it like this. Okay. So if you think of this condition, you know, these kind of OR conditions are not so nice when we sort of like Fourier transforms and real numbers. So let's write this as a real number thing instead. So I claim that in fact the OR of these things is this thing, in the sense that this is 1 if the OR is true and this is 0 if the OR is false. Okay. This is in fact the 3-bit Fourier transform of the OR function, if you want it. What? 7, yeah. Yeah, this is the Swedish thing. You have this little, I can't, that's a 7 in the US, right? But that's, So now you want to say, well, you want to say, if this accepts with probability greater than 7/8, then in fact the expectation of one of these things has to be big. Okay. So let's do it first in the very simple case, when we had the same distribution essentially except for the minus sign and the parity. So what can you say on the expectations of all these terms? By this, I mean this distribution, right? So the expectation of f of x, what's the expectation of f of x? Why? Pardon?
Uniform distribution.
Yeah, it's x is uniformly distributed, and we have folding, right? Yeah. How about this thing?
Independent and folding.
Yeah, but they're in fact independent and we have folding. Okay? And z is the same, we just agree that they're symmetric. So how about this term? Are y and z independent? They're not independent, right? Because things that project onto the same thing are... But in fact, I claim that if you look at the input x, y, z, and minus x, y, and minus z, they're in fact equally likely. Because, if you just change x to minus x, you change z to minus z, and we have exactly the same. And in fact, these terms will cancel each other because, x doesn't appear, and so this means that, since we can take care of all terms except possibly the last term, if the acceptance of this is higher than 7/8 by, set that 7/8 plus some gamma, this means that this, well, we have a minus sign. This means that the expectation of this thing has to be big, right? And, we actually get the minus sign, which is exactly the minus sign since I changed the z. So now we have exactly the same situation as we had with the parity, right? All the other terms disappear, and that's it. But now we have this distribution instead. Okay, let's... we have this new distribution, which is the one over here. Let's call this distribution d sat. So now we took. So before I just took care of all these terms. What happens to these terms in this situation? I said if we had the parity distributions, this was the only guy that we needed to care about, right? What?
Just get one more.
Yes. So let's. So we still had, both independence, between x and the y and x and the z. Okay. So I claim that already this term will give you problems. Okay. And I had planned to do this, but time is up. And it might even be so this is now homework until tomorrow. We meet tomorrow at 11. Okay. Start estimating this term and see how far you get. We need to prove, right? The way to prove, first of all, one bad thing is we just have the long code of one of the tables. We're never going to extract. If this term is big, we will never extract the strategy of the two provers, it seems, right? Because we only have essentially one side. We have a g which only lives. Some of the distribution of y and z will tell you something about the smaller table. But the question is, can you use this in such a case to extract a strategy? So just so that how would you go ahead and estimate this value? Just the first step in the calculation. Can anybody guess what that would be?
Fourier transform.
Yes, you should expand the Fourier transform and then take it term by term and go from there and see if you can do it term by term. Okay, so we'll continue at 11 tomorrow.
Yeah,